welcome to another show on teaching physical science. Today we're doing grade 12 rates of reaction, and we're joined by John. Hello, John.
Hi, Helen. It's good to be here.
It's good to have you back. And of course we have Dylan behind the computer controlling all of the buttons. Now, John, I know you've been here before, but for those of you who haven't seen the previous show, why don't you tell us a little bit more about yourself?
With pleasure, Helen. I grew up in Durban. Did my high school education in Durban and then went on to Natal University, did a BSc, studied maths, science, maths, physics and chemistry, majored really in chemistry and maths. Chemistry was one of my favourite subjects, and then went on to HTE, taught at a couple of schools, taught for about 17 years, different schools around the country, both private schools and state schools, and then got the opportunity to join Mindset, and that was almost 10 years ago.
Sure. And of course you were teaching science at that time.
Physical science. I did occasionally dip in, depending on the timetable, to a maths class. So there were different times that you would adjust and adapt, but there's such a crossover between maths and science. I mean, maths is really just a tool for doing science, isn't it? No, we won't get into that debate.
No.
Just to throw it out there, my bias is obvious.
Yeah, well, mine is yes. Before we go into the content, just a reminder to everyone who's out there, you can join the conversation with the hashtag VTScience. That's VT and then the word science. Shall we start with grade 12?
Sure. This topic, rate of reaction, or rates of reaction, or reaction rate, is part of the bigger topic, which is called chemical change. It fits under that. And it's really quite interesting because it picks up a whole lot of fundamental chemistry that learners have dealt with in grade 10, grade 11, and now in grade 12. So it's a consolidation of much of the previous work that they have already done. And probably what's critical to this understanding of this section is writing chemical formula, writing balanced equations, all of those good, solid, fundamental chemistry things. And in some ways, it's quite an easy section. Generally, when we look at the exams that have happened previously, before CAPS, the rates section was kind of not very difficult. And the exam guidelines for CAPS don't seem to indicate that it's going to be much more difficult. It's much more of the same that what we've had previously. But it is a very interesting section. And I think it's a section that if it's taught properly, it can really stimulate learners' interest in the subject. And it's quite fun, it's quite exciting, and if you don't underestimate it, it's got the opportunity to access quite a few marks without too much difficulty. So you don't often find level 4 questions in rates of reaction. Those are left for later. But I would suggest that it is really quite an important section because it ties together and it forms the basis of many other sections. Particularly if learners go on to university and study chemistry. Rates of reaction are studied all the way up until honours level and probably even masters, where you get mechanisms of all sorts of things happening. But at school level, this is a chance to engage learners, get their interest, and really get them to believe that they can do chemistry. And if they get that sense of self-belief, it makes it so much easier for them moving into the next section, which is chemical equilibrium, which is really quite conceptually difficult.
Okay.
Does that...
Yes, you say give them a chance to believe that they can do chemistry, but now I'm a grade 12 student. I've never really been able to do chemistry prior, whether it's because of inactivity in my classroom or possibly poor teaching, whatever it is. How can I get to the point in this current section with poor prior knowledge to
that's a really good question, and I think it takes a spark, because a lot of chemistry is a lot of learning, and there is some rote learning. Let's not get away from that. But having said that, it's no good trying just to rote learn everything. That's really demotivating. And what I think is critical, and this section provides it, is that if it's taught not as a rote learning section from the textbook, but if it's taught with intrigue and incitement and questioning and creates some curiosity, that gives far better motivation for the struggling learner who hasn't really grasped grade 10 work or even grade 9 work, where you were supposed to learn the names of the elements and the symbols from the periodic table. Now, nobody can learn that for you.
Yes.
Unfortunately, you have to go and learn that sodium has a chemical symbol of Na, however it sticks in your head. But once you've learned it, you'll never forget it. So it's important to get over that threshold of opposition to learning. And it's actually quite interesting because it forms an analogy to one of the ideas in the section, that a chemical reaction can only take place when there's enough energy, when there's a spark to make things happen. And so I would see this section as an ideal section to really motivate your learners, particularly the ones that are struggling. Give them an opportunity to go back and look at where they've misunderstood.
And what should they go back and look at?
Okay, so for me, if I were starting out and looking at preparing this section, I think it's essential as a teacher to know where your learners are. And so a baseline assessment of some sort is a necessity.
Would you recommend a verbal or a written?
No, I think a written thing is often more useful. It doesn't necessarily have to be a test, but it can be something that learners do in their own time even. So it could be a homework activity that's handed in. So you can assess and provide some sort of diagnostic understanding of where your learners are at. Because they're not coming to grade 12. I mean, you put yourself in the position as a grade 12 learner that hadn't for some reason done too much previously. Now, if I don't know that, then I'm not going to, as the teacher, remedy some of the issues.
Yes.
So I need a diagnostic. And for me, the writing of chemical formula is something that you can't, in any chemistry class, ignore. Something that you would start in grade 10 and you'd repeat in grade 11 and you'd continue in grade 12, because what's the purpose of learning the more difficult stuff and then learners don't do the correct calculations because they've written the formula incorrectly? And this is going to be particularly important this year, because in the exam guidelines for CAPS, it's made a very clear stress on quantitative chemistry being examinable, which wasn't the case previously. So things like stoichiometry, which is really writing the correct formula and balancing the equation, those sort of calculations can be introduced and they can play a role. So although we've said rates of reaction are generally easy, it's possible that having done a rate of reaction, one could have a calculation that follows it, asking learners to calculate the yield being the mass of the product. So given a certain amount of reagent or reactant. Now I'm using those words quite freely, and that's the other area that I think that learners don't spend enough time on, apart from writing balanced equations and being able to write chemical formula and understanding what's happening there, is they don't understand all the terminology. And as chemistry teachers, as science teachers, and even as textbook writers, people tend to use terminology interchangeably.
Yes.
And that creates all sorts of confusion. So a reagent, a reactant, yes, they're the same thing. But unless somebody explicitly said to you what a reagent is, what a reactant is, it doesn't make sense. And so we talk about products, and we might be thinking, well, products are something that we do in maths when we multiply things together.
That's what I would think.
Whereas a product in the chemistry classroom is dealing with the outcome of a chemical reaction. So if we have a left-hand side of of a chemical equation, all the reactants are on the left-hand side, and all the products are on the right-hand side of a balanced chemical equation. And so there's some terminology that I think is critical for learners to revise. From grade 11 work, they will also have been exposed to the idea of chemical reactions that produce energy, and chemical reaction, excess energy, shall I say, and chemical reactions that absorb energy.
We spoke about this briefly in the last
Correct.
show. Yes.
So we revisit that. We revisit the idea of exothermic and endothermic reactions. It's done in grade 11, might have mentioned it in grade 10, but now it becomes really important for us to classify reactions as being exothermic or endothermic. And the additional little bit of a jump that we add on in grade 12 is to look at the concept of enthalpy. Now, it's bad enough having to say it.
I had to Google the word earlier to find out what it was.
It's not an easy word to say,
no.
Not easy word to spell. And if you don't get it right, a lot of textbooks didn't used to use the correct word enthalpy. It used to be called heat of reaction, or simply delta H. And I suppose in the end, at the bottom, final analysis, delta H is what most learners are going to refer to.
Yes.
But it's important to know that word, because the question could ask about enthalpy, and if you haven't seen the word enthalpy, you might be in trouble. But the concept of enthalpy is really just the difference of the energy of the products and reactants. We need to revise energy profiles that are taking place in a reaction. Now, energy profiles are a way of representing what's happening during the course of a reaction from an energy perspective.
Okay.
And it's quite interesting that learners are introduced to that in grade 11, but it needs to carry on into grade 12. And there have been questions in previous NCS exam papers that have dealt with the energy profiles. I'm sure we'll talk a little bit more about the representation that comes about there. But so those are some of the critical things that I think are important.
And this is all pre-knowledge that you're talking about?
It is pre-knowledge.
Prior knowledge.
It's prior knowledge. The other aspect of prior knowledge that I think that it is essential to get to grips with, and that's something that learners have probably been dealing with since as young as grade 5 in natural science, and that's the scientific method, and how to set up a reaction or an investigation, how to ask an investigative question. What is a hypothesis? What are the variables? Which is the independent variable? Which is the dependent variable? All of these types of questions have in the past been covered by questions in the final exam on rates of reaction. So when you teach it, because it's so practical, and because, as I said to you, it could be the spark that gets learners working, introducing an investigation, I think, is an ideal way of dealing with it.
Yeah.
I've brought something along, so I don't want to let the water get too cold.
Yes.
But just to illustrate what I mean, if I may.
Of course.
At
Can
this
I
point,
touch on one thing
yes,
very quickly? Right at the beginning of this very informative talk that you've just given, you said that they should possibly do a homework exercise to assess their prior knowledge. I think that's a really valuable thing, considering the amount of prior knowledge that they
Yes.
need to go over. And what's so valuable about it is they could then consult old notes, and it almost becomes a revision exercise in itself. It's not just an assessment. So
I'd agree with that. Yeah.
yeah.
The important thing here is I think that this section is often underestimated. It's seen as an easy section, and although it usually only in the exams covers level 1, 2, and maybe a stretch 3, it's usually quite easy. But learners don't give enough attention to doing the work. And I think sometimes teachers rush teaching it as well.
Yes.
Because it's seen as an easy thing, let me rush through this section. The learners can catch up with reading the textbook, but it is really important to put the building blocks in place, because there are some difficult concepts, and there are some conceptual difficulties that are not just chemistry related, but language related as well. I mean, we mentioned the word product. Here's another one, the very word rate. Now, in mathematics classroom, which most learners will have come across the word rate, they'll have dealt with it in terms of speed and distance and time.
Yes.
A per, and the idea of per, where here we're talking, yes, we can measure rate of reaction like that. It's the amount of product produced per second, but there's more to it than just a number. And so one needs to understand that there's a lot more happening when we look at any chemical reaction, because when we talk about rate of reaction, we're really talking about how quickly and how much stuff can be made under various conditions. So it applies to everyday life as well.
Yeah.
Why does milk go rancid? It's because of a reaction that's taking place.
And that all applies to this section.
Exactly.
Yes.
Now, the one thing that learners sometimes get mixed up with is how quickly we go from the starting point to the end point to a comparison about how much product we produce. So
I can see how they would get confused.
it's very easy. And even in our language we sometimes do. Now, the word that we use for the amount of product at the end, final amount, that we refer to as yield. And in the documents we even talk about rate and extent of reaction. And extent of reaction really refers to the yield. How much have you been produced? Now, yield is a really important economic factor in chemical industry, chemical engineering, because if you've got a gold mine, you want to know how much gold you're going to produce at the end of the day. What's your yield going to be? If it's going to take too much money to get a piffling a little amount of product, you're not going to be wanting to invest. So these are some of the complications, and these are some of the uses of words that come up into this section that are often used in everyday life.
Yield is another one of those terms that has a different meaning.
Exactly.
In
So,
real
I
life.
mean, in real life, we talk about a yield sign driving down the street. So, what's that got to do with?
I can't find a comparison now.
No.
No.
But one can understand this English word that has a specific meaning in science, that one needs to recognize that it can be quite difficult. We can't just throw this vocabulary out without explaining it carefully, and so even though we think it's easy, it can be confusing.
Yes. Well, while you set up your things, I'll quickly talk about our guest last week. Spoke quite a bit about language, and before the show, we were talking about language as well. And he said something quite profound. I'm sorry he didn't say it on the show as well. Said that people try and compare the English language to the scientific language, and really, the scientific language should be treated as its own individual language because they're so different. And when I hear things like yield, I can see his point that
Yes.
learners should have a list of words that mean different things. And
Absolutely.
okay,
Okay.
so what do you have in front
Okay,
of you?
so I've got just a little, 3 little beakers.
Yes.
Okay, and in this beaker, I've put a little bit of dishwashing liquid. This one I've put it into warm water, so it's floating in the warm water. This dishwashing liquid I've put into some ice.
Okay.
Now, over here I've got some hydrogen peroxide, and I'm just going to add a little bit to the one in the warm beaker and one in the cold beaker. I should really have measured them and made them the same, but that's not what I'm worried about. We're just going to leave it. And as I was saying, Helen, the idea of rate of reaction is to enhance that curiosity. So as a teaching strategy, apart from talking about why certain reactions happen, so we have a piece of paper on the table. Why isn't it bursting into flame? It's carbon based. We know that carbon burns.
Yes.
We know there's lots of oxygen around in the room, but why isn't it spontaneously burning? Now, that creates a bit of curiosity.
It does.
And I mean, even putting up something like this in front of a class and just leaving it, saying, I want you just to watch, and we'll look at it at the end of the lesson, and just creates a little bit of a kind of a, oh, that's interesting. Gets learners to ask the question. Now, I'm going to add to this one a small amount of hydrogen peroxide as well. Now, just the hydrogen peroxide isn't reacting with the soap in any way. The soap is just there because it's capturing some bubbles. And I don't know if you can see them over here in the smaller beaker a little bit better than in the bigger beaker, in those beakers, because it might be a bit. This one, there's a little bit of bubbling happening.
Yes.
But in this one, we can see there's a little bit of foam that's started over there, a bit more, because it's in warm water. So in the cold water, one could perhaps say that there's not as much.
No, you could definitely say that.
And in this one, yes, there's an in-between amount. So why is that? It's the same stuff, but all we're doing is we're controlling an external factor. We're changing the temperature. And so one could start to change other factors, to say what makes things happen.
Now, in a classroom, would you get them to do this experiment themselves, or would you have it in front of the class?
It depends. I would recommend that if you, depending on the amount of equipment that you've got, I mean, dishwashing soap and containers and hydrogen peroxide, all very freely available.
Yes.
It doesn't cost a lot either, so it's possible to do it. I like to have a demonstration and then give learners something different to go and investigate on their own. So, for example, I might show them this reaction and then say, but now, how can we apply that to a problem, a local problem? Like, we know that when we come into school, we recognize that there's a bridge that is rusting. So what could we do to maintain the bridge? Is there a way of slowing down a chemical reaction, the reaction of oxygen and the metal. So what can you do? What about another environmental problem? We know that we have access to compost. Is it possible for us to harvest some of the methane gas from that compost and to create biofuel? These are all questions that have a problem.
Yes.
That has a solution. Now, you could even include something that's a little bit more technological. You could give learners, and maybe it's not even beyond the scope of work within a school, to create for younger learners even, to say, here's a challenge for you. Take some simple stuff like bicarbonate of soda and some acid and build a rocket that can be used to fuel a boat that moves across a river.
You see, the mother in me is screaming, don't do
No,
that.
I know.
What kind of acid are you talking about?
Hydrochloric acid or even lemon juice would do it.
Okay.
Yeah, so I mean, vinegar. Yeah.
No, lemon juice is nice and freely available.
Yeah.
Hydrochloric acid, a little bit more difficult to get.
But I mean, it is available because of pool shops and that sort of thing. But one would need to be careful. So
Yes.
It doesn't really matter what the reaction is. Getting learners to understand that there are chemicals that you can react together to produce an outcome. And if you make the reaction go too quickly, it's not going to be profitable. If you make it go too slowly, it's not going to be. You want to find the ideal rate to get an outcome. Now, I've got to do one other thing.
Yes.
Because you can't just have that sitting there and looking like it's just yellow soap and not doing much green soap. You don't have to worry, Helen. It's not going to explode. You are quite safe.
Did you notice me rolling back just a
I
little?
knew that you were rolling back. I'll just take a little bit of this stuff. Now, there's other stuff that you can use, but I'm using some manganese dioxide, and I'm going to tap a little bit in. Now, we've kept the hot water one going, we've kept the cold, and we haven't seen that much happening in terms of foam. But I'm just going to tap a little bit of that in, swirl it around, and just leave it for a few minutes. But already I can see, just with those few little bits of powder, I hope you can see, that I've already got a finger full of foam on the side there.
Yes, you do.
It's more than what I've had in all the time that these two. So what did it do? This is acting as, and if you look inside there, you can see the foam is just forming on the top of the surface. Look on the side, it's just bubbling away, and it will produce more and more. If you have a higher concentration of peroxide or a dilute concentration, you can compare the effect of dilute and concentrated. What we've added there is just something that is called a catalyst. It's reduced the amount of energy that we require to produce the decomposition of hydrogen peroxide. And it's quite perfect. It's perfectly safe. It's only, those bubbles are just bubbles of oxygen in the soap.
Okay.
Now, we could use other catalysts which are more effective. So you could use yeast to make oxygen, and produces a huge volume of yeast. I didn't want to spill over too much. So that's another option. Even parts of chicken liver, there's a catalyst, there's a what do we call it in a human or in an animal? It's not just a catalyst, but it's an enzyme. Okay. There's an enzyme in chicken liver that allows for this decomposition, and it produces huge amounts. It would have actually bubbled over and caused but you can see after.
With the same hydrogen peroxide
Yes,
and the same.
yes.
That's another thing that's easily accessible. Something cheap. You
Yeah.
could.
So the idea here is to show that we're getting the same reaction under different conditions, and part of our understanding of chemistry is that we're beginning to recognize that we can now control things, and that's the important thing. Chemistry isn't just about fireworks and burning fuel. It's about being able to make things economically, effectively, cheaply as possible, shortest amount of time, so that we can sell a product to make money. Well, that's what the motivation of the chemical engineers is,
Yes.
and the industrial chemists. And hence we've got a very successful chemical industry internationally. And that's driven technology. So this section of work that we're talking about has actually had a huge impact in everyday life. It continues to have it. And my challenge to learners is to ask them to look for examples in everyday life where they notice reactions that go quickly,
Yes.
reactions that go slowly, reactions that are useful to us, reactions that are not useful to us. How can we slow some things down? How can we speed them up? There's a whole cosmetic industry that's been developed, which I'm sure you're aware of.
Yes, I am. I'm quite thankful for it.
To slow the effects of aging.
Mm.
That's rate of reaction.
I'd never considered it like
Yeah.
that, but of course.
It's a chemical that's inhibiting a natural process. And so our understanding of this section of work has so many implications. And so I really think that it, in many ways, can be like this little powder that I've added to our learning of chemistry. It can be a catalyst for us to achieve more.
Yes.
So, the thing is, chemistry can be fun. Yes, there is some hard work, there is some rote learning we have to do, but given a curiosity, given something of interest, something that sparks an interest, that says, oh, why does that happen? It can be motivational as well. And certainly that's what I would encourage teachers to use this as a platform to not slow down learners' interest where the reaction tends to not do too much,
Yes.
but rather to add a catalyst, to let this be the addition of a catalyst. Now you can see there's a little bit more foam, although the water's lukewarm, but certainly more than in the... But when we add the catalyst, look how much there's. Now I know it's not a fair comparison because the beakers are different, but in relation, there's much more foam that's been produced because of the catalyst.
I like your analogy. I like it a lot. 'Cause in my head, I'm thinking, okay, what a good teacher would do as opposed to one that really wants to inspire. And the one that really wants to inspire would be like that catalyst that would
Exactly.
foam it up.
And you see, I think the thing that we also need to understand in teaching this topic is I would say that even good teachers teach the subject well. They get across the correct concepts. But your outstanding and exceptional teachers don't just teach the subject, they teach children.
Yes.
They teach the learners. And it's being there for those life lessons. And matric is stressful. The grade 12 year is a stressful year. The more life lessons we can give learners in their matric year to help them understand how they can cope with the real world, I think that's we're doing a disservice if we don't do that.
It's really their last chance.
Exactly.
To get it.
Because when they get out of school, yes, they could find things out for themselves, but they're never really going to be in a captive, nurturing environment.
Yes.
As a captive part of a captive audience, or as as an association, as a group of a cohort of learners, friends they make there, having learned it from each other, the relationships that a grade 12 learners, a class builds with their teacher, I think is something very special as well, because they have clear objectives, teacher has clear objectives, and it's about the teacher using the correct tools of motivation, because for many of them they're adults, but they're not recognized as adults.
Yes.
They're frustrated with their parents because their parents don't understand often, and so who do they talk to? Who do they confide in? Most people would say, well, that's not my job. That's the English teacher or the life orientated teacher's job. But I honestly believe it's one of the important things that makes the difference between a good and a great teacher.
Yes.
Is that attention to where the learners are at, not only from a content knowledge point of view and a skills point of view, but their emotional environment, getting to know them, getting to motivate them, and motivate them in different ways. Because some learners will be motivated by reward, some will be motivated by negative consequence, others will be motivated just by curiosity.
And of course it's balancing all of those things.
It's putting all of that together.
Yes. I want to talk a little bit more about this. In my head, if I were teaching this, what I'd probably do is introduce it at the beginning of the section and then send them out to find examples of that rate of reaction in real life, whether it be the rusting bridge or an anti-aging commercial with various research to back it up. Not so much for them to have extra work, but for them to recognize it. So they need to submit something at the end of it that shows that they have recognized it.
And that could be something they submit with a photo from a cell phone.
Yes.
There are endless possibilities. Now, I don't want to say that that's all fluff, but there is some core teaching that also has to take place.
Yeah, very definitely.
Yeah, and so one of the things that I would like to reiterate, and I've started again by showing this as a demonstration, I've shown a macroscopic view, just to remind people that perhaps didn't see the previous session. May I just move this for a second, because what we've looked at is we've looked at the macroscopic, and it's very clear that it's a big world. We can see it, we can touch it. But in teaching chemistry, there are really three things that we need to be clear about. We can start with macro, which we've observed, but then to look at the micro. And this is just as important, and it links to the two. Because we can talk all day about what's happening and why, and we can identify. So we could identify factors that change chemical reactants, not just temperature, not just the addition of a catalyst. Understanding what the catalyst is actually doing. We need to get down to the subatomic or even atomic level, the microscopic, and try and explain why things happen. And this leads us into some theory in this section called collision theory.
Okay.
And now, if we look at collision theory, it's really all about molecules colliding. One of the things that I've done with this, before there was simulations and things on the internet, and in the presentation I'm sure later we'll come to see that there are some great simulations you can use to show both in video format and on FET, but we'll get to that, I'm sure. But one could dramatize this, suggest to learners that some learners are one molecule and they're having to move around, bump into each other, and one can create it up.
Yes.
Yeah. The faster you're moving, the slower you're moving, what's happening? What's the things that's making chemical bonding possible? collision theory is very important. It's important that learners learn that. It's not a difficult thing to understand.
I actually heard of a teacher recently who taught this by using a dance party within their classroom. And
Excellent, wonderful.
yes.
Yeah. Now, the third aspect, and I think it's important that we signpost for learners that we are moving from the macro to the micro and then to the symbolic.
Now, symbolic would then link to later sections like the, it's slipping my head right now.
Chemical equilibrium. Yeah. And in symbolic, what we're really going to be looking at is chemical equations.
Which are, of course, are impossible to do if you don't know your periodic table.
Correct. And the other aspect that links very nicely here is the whole emphasis on graphs and interpreting graphs. It's a skill. It's drawing, observing, graphing, analyzing, reporting, concluding. That whole process follows us around. And so I see this as another example of taking Johnson's triangle and really embedding learners' knowledge and building those building blocks so that they're confident. A lot of learners get, shall I say, apprehensive about chemistry and writing a chemistry exam because they're not confident. I think that's true of any subject. So this is a real confidence building section. If we can build their confidence, reassure them, motivate them, they'll be ready for the next section.
Good. Well, shall we take a look at your pressure points that you set out?
Sure.
Oh, sorry, very quickly, before we get to that, we do have some mindset resources. Let's say a teacher's not confident in the content and they want to just brush up on their own skills. We have a list of links which I'll put into the blog, and I watched one this morning to try and figure out what was going on, and I felt quite informed by the time we got to today. So I'll post that up on the blog.
Yeah, I really do think that the video series on rates of chemical reaction and equilibrium, it's under the classroom resources section, is really good. And it definitely is an advantage to use because it shows some of the practical investigations.
Yes.
So we've done just a silly, like a flashpoint, a thing to get learners' attention.
Yes.
But there are other experiments. There are many other experiments, investigations that I would encourage teachers to do with their learners and get learners to do them. And those are illustrated very nicely in that video series as well.
They are.
Okay.
Okay, so I will post those up on the blog. Let's go to your 3 pressure points, which...
Okay.
Sorry, 4 pressure points.
Yeah, sorry. I 3 was just...
not quite enough.
Yeah.
Yes.
So I think I've mentioned most of them already, but just let's highlight them. The importance of chemical equations, recognizing that the writing of formula, and I don't think that one should leave that totally to learners. Giving them opportunity to practice, giving them opportunity to test themselves on these type of things is really important. It's routine, it's drill and practice, but it needs to happen. Without it, I think that we're doing a disservice.
Yeah.
The second thing that I know that comes up in this section is the scientific method, and we've briefly alluded to it. But learners really do struggle with writing a hypothesis, identifying variables, understanding what a fair test is, that you can only have 2 things that are able to change. Everything else has to stay constant. So in the example that I did, which was probably not very good chemistry, I should have used the same amount of reagent in each of the beakers.
Yes.
Although it doesn't really make a difference. But if I was being absolutely pedantic about it, I'd need to do that. Use the same size of containers. Use only thing that would be different would be the difference in temperature.
So that's the only change.
So you can see then the effect of temperature. You can see if you were changing concentration of the reactant, then you would say a 5% solution, a 10%, 15%, 20%. Have a look at the difference. By looking at it at different concentrations, you'll be able to say, I've controlled the concentration. Concentration's the independent variable. So what's the outcome? That's the time it's taken to produce a certain amount of. And one could measure that in terms of a set of test tubes, or even a little microchem kit. You could measure the amount of foam that. So use a stopwatch until it gets to the top of to a certain level. You don't need fancy equipment. There are many experiments you can do.
Then you've got graphs.
Graphs. Now, graphs, it's just plotting graphs, and there are different types of graphs depending on what you're measuring. So, as I've suggested there, we could be collecting the amount of product, so amount of foam that is produced above a test tube. That could be a measurement after 5 seconds, how much, after 10 seconds, how much you got, after 15 seconds. You then plot a graph of the amount of stuff that you've collected against time. The skill of labeling axes, putting a heading in, plotting the points, drawing a line that shows the trend. All of those aspects are really important. Being able to interpret the graph as well, because not every graph is going to be the same shape. For example, you could measure the mass of your reacting vessel, starting off with a big mass. Then you add, so let's just take an example of zinc metal, put it into a conical flask, onto a beam, onto an electronic scale, add some hydrochloric acid of a known concentration, and then measure the mass after 10 seconds, 15 seconds, 20 seconds, and so on. What's going to happen is, because the conical flask is open, hydrogen is going to be released into the atmosphere. So the shape of your graph will be different. So in the previous graph that I mentioned, where we're collecting foam, or we're collecting gas, then we're going to get a graph that looks like that.
Okay.
So this is the volume of gas, and that's time. The one that I've just been mentioning, where I said let's look at mass against time, you're going to start with a bigger mass and you're going to decrease. Learners need to understand that those could be representing similar types of reaction. Now, the link to maths in this section, and it's quite interesting that calculus is introduced more or less at the same time, is we're talking about rate, and you're looking at the gradient to the curve.
Yes.
So you haven't got a constant rate, but the rate is changing. At this point, you need to recognize that the gradient is zero. So the reaction has come to an end.
I think that's an interesting comparison to do within the classroom, because the learners are doing calculus at that same point, and not all maths teachers know really what calculus is used for. They can do it, and they can get a child to get 100% for the section, but understand what it's used for.
Look, we're doing it very intuitively in chemistry. We're not going to ask them to do the derivative of this graph at a particular point. But it's important that we need to recognize.
I have a question.
Okay,
yes,
Dylan, he speaks.
I am real. I'm here. you've just said, John, how important then, in order to establish the fact that maths is the language of science, should maths teachers and science teachers be talking?
Absolutely. I think it's very, very important that in a school we tend to see them in silos.
Yes.
But I don't think that that's worthwhile. I think that the leadership in the school needs to encourage collaboration. And particularly when we're dealing with this, because in terms of that, you don't want your science teachers to mess it up for your maths teachers.
Oh, please no.
But at the same time, you want to be able to use the tools in science. And so I think it's a very valuable point that science and math teachers, they do need to talk, and they do need to create activities together. I mean, I have colleagues that are maths teachers. I know that having taught a little bit of maths myself made that a little easier. But we did some amazing things as cooperative learning. It doesn't have to be every lesson.
Yes.
Well, once a term, put the maths class and the science class together, and have two teachers in the same class.
At the same time, then the learners can't play you off each other
Exactly.
and tell you, no, my maths teacher hasn't taught me this.
Exactly. And so one could do a whole number of investigations and applications where maths and science can really do things that, because the very fact of plotting graphs, and I think that's a critical thing in junior classes, to build that through the school as well. I really do believe it's fundamental. I know that in schools that I've taught at, we followed a program which is, don't want to get too far off track, but a program that was called CASE, and there was a maths similar program called CAME. It was cognitive acceleration through science education, cognitive acceleration through maths education. And it had amazing impact in both those subjects as well as in English and other subjects, because it became a catalyst for the school to work together to a common goal. And that was to improve learners' understanding, allowed teachers to reflect together about how you teach things and how I teach things and how we can teach them better. And for me, that's the conversation that needs to take place. It's pointless science needing learners to have a certain math skill, and it's only taught 3 weeks after they need it.
Yeah, well, that happened with NCS, I think.
It did.
Grade 10 trig was needed in science before it was taught in maths.
Exactly.
Yeah.
So those are some of the areas that I think that by talking and making arrangements and understanding where learners are, don't just assume that your learners are up to speed with their maths if you're in a science class. That's also, I think, a terrible error of assumption that teachers can make. Just because they're supposed to be there, they might not be there. They might not be ready for it.
Yeah.
Okay, so
we are running a bit short on time, so we're going to rush through the next few slides. The next one is good ideas. Now, this is a new thing that we've introduced to try and encourage where small errors are made by some teachers that could be better with small changes. So you've drawn up a list of 3.
Good. I think I've spoken through them.
Yes, the macro.
So the macro idea of starting with a demonstration, then to explain the observations through a micro, and to model that, so that it's not just dry theory. Use simulations, use animations, use drama, use whatever you want to, but use cut out pieces of paper so that learners
So don't just go for the rote.
Don't go for the rote.
Immediately for something that they can relate to, or see, or touch, or feel, or yes.
And then I think the other thing is to get them to record a real investigation, follow through. And they could do that in groups. They could do different groups, could do different investigations. Like, what's more effective in terms of like antacid tablets? How could you make your antacid tablet more effective? Well, would it react in acid, because it's going to react in the stomach in acid, if it was in smaller pits? Would it react if the temperature was higher? Would it react if it's colder? All of those sort of things. Just having said that, the size of particles, it is an area that I don't know why, but I've known over a number of years, learners really battle with the fact that smaller particles have a bigger surface area, and they don't somehow get that. So if you have a block like that, it has a certain area, but now if you take the same thing and you break it into smaller bits.
Okay, I do understand that. Do you mean it's got the, and I'm not too sure if I'm using the right term here, but the same volume, but broken up?
Yes.
Okay.
And because now, at the surface, when we have a chemical reaction, this is the only surface that reagents can stick on. But now, reagents can stick on in between.
Yes.
They can stick on in between those. So if we break them up into smaller and smaller particles, we're increasing the surface area. We're not just having the top surface, if that makes sense. But I know that learners battle with it. And their statements are often confused about, well, what increases the rate of reaction? Increase surface area. What do I have to do? Do I have to increase the size of the particles or decrease the size of the particles? And one needs to get it the right way around.
You know, the way I used to think about it when I was in school was I used to think of it as a suite. And this suite, you've only got 4 sides to lick on. But this suite over here, you've got a whole lot of different sides to lick on. So you've got more.
Exactly. Lovely.
Yeah.
That's lovely. Yeah. So, getting that across in whatever way I think is important.
Food always works for me.
Okay.
Yes, and your last one, I think we've
We've
spoken
about it.
Record observations.
Yes, and develop the skills. So the graphing skills, the identification of variables, the
and tie it in the whole
the
time
whole thing
with
comes
each
back.
other. Yes.
So it really does fit together.
Okay, then we've got the 5-point teaching summary, and you have once again touched on most of these already. We've got demonstrate different rates, which
we've done. Introduce the micro, the collision theory. Go through the detail of that. I'm not going to go through that now.
Yes.
Calculation of rates, but that can be by observation, like we've suggested, measuring and drawing graphs, calculate.
And there were the two different rates,
two
the
different
yield and the
correct. There are 2 different graphs.
Okay.
So the graph that went upwards and the one that went downwards, and the yield being the final amount, and the rate being at individual points of time through that process. So understanding the difference between those. And then, as I've said to you, give the learners the opportunity to go and investigate factors. And the factors that we really are looking for is the effect of temperature, concentration, size of particle or surface area, the effect of a catalyst. And those are the main ones that they need to know. So it's not a lot of learning. It's quite accessible. But we need to consolidate that with exam questions as well.
Yes.
Make sure that they get sufficient practice.
Now, no one wants to teach towards exams, but at the same time, they're writing exams in 4 months, 5 months' time.
Correct.
Yeah.
And in this section, I think what's really important is for learners to not waffle. They need to get to the essence of what needs to be said and be conservative in the amount of words they use in their explanations.
Yes.
Because to explain something simply in as few words as possible is actually more elegant than waffling on for a page and a half.
Yes.
So I would encourage learners to look for the elegant solution.
Yes, it reminds me of a statement my dad often says, I like my dad quite a bit, and he says as soon as you add adverbs into anything, you lose the meaning. So all of your words that end in ly,
Yes.
yeah, you should really, all of those words, lose it.
Okay.
Well, that was quite comprehensive. We have a tiny little bit of time left to do one last thing. Let's take
do
a
it.
look. Okay, in our first week we spoke about the no opt-out, which is where every child who's asked a question has to give an answer, and preferably it had to be the right answer. And we spoke about different strategies that we could use to do this. Last week we spoke about right is right, and right is right says that you can't accept half-right answers. You must always push until you get the fully correct answer. Some of what he said was slightly controversial, and I wasn't sure if I agreed with it, but we'll leave that conversation in last week's show. This week, we are talking about Stretch It. It's from the same book, written by Doug Lemoff, and it says the sequence of learning does not end with the right answer. Reward right answers with follow-up questions that extend knowledge and test for reliability. This technique is especially important for differentiating instruction. Okay,
It's quite a mouthful.
Yes, it is, and I'm quite impressed. I read it without stumbling. Basically, what it's saying is that there shouldn't be a sweet at the end of the right answer. The reward for it should be extending the knowledge into either another context or extending it into more in-depth knowledge, depending on the type of question you've got going on.
Well, I think this section, and we did kind of touch on that, is to get the learners to become more aware of where they can see things in the real world.
Yes.
So take what happens in the classroom and stretch it. Find the bridge from the classroom to the real world. And so
exactly
that's exactly what it's saying. Yeah.
Yes.
And that's a reward in itself. Yeah.
Like, even while you were speaking about this, I got this image, speaking about rates of reaction, I got an image of almost like the spider where it just connects to everything else and touches everything else. And this technique suits it very well.
Excellent.
Yes.
I think it's something that's very practical and certainly is worthwhile doing it. So for this week, stretch it.
Yes. If you would like to send us any thoughts on this, please tweet us during the week with the hashtag VTScience. Remember that next week we won't be having a show because all of us are on holiday. Well, not us, but teachers.
Yeah.
Yes. So enjoy the week off. Spend some time watching some videos, getting to grips with the content ahead. And we'll see you in 2 weeks' time on the 8th of May, where we'll be looking at grade 10 content.
6th of May, Helen. Say 8th of May.
Yes,
sorry.
6th of May is
maths.
Yes. Thank you very much, John, for joining us.
It's a pleasure.
And for the experiment. It's good to do something different.
My pleasure.
And thank you, Dylan, for the magic, both behind the buttons and with your questions. Join us soon. Bye.